And we're back, and I think this third video about multivariate distributions will probably finish this short series up. So we want to look at definition 3.7 out of our textbook, and it's for a joint continuous or cumulative distribution function. And we're going to continue to let x, y be discrete random variables, and we will have a joint cumulative distribution fxy if that's equal to the probability that x is less than or equal to the x right here, and y is less than or equal to this y value. And that's what we mean. And here's how we calculate it. We would have to sum over x less than or equal to x sigma y less than or equal to y f of x y. And that would be for the discrete case. Now definition, we'll play with that at some point. I'll work some problems for you. But definition 3.8 gets us into continuous random variables x and y. So for continuous random variables x and y, f is a joint PDF, probability density function, if and only if the probability that the ordered pairs x, y are elements of some region A is equal to the double integral over the two-dimensional region A f of x, y dx dy. And this would be, the A would be a region in the x, y plane. Now we might as well jump right into an example to see what that definition means and how all this works out for us. So let's look at example from our textbook again, 3.50. And let's suppose that we have a joint PDF that looks like f of x, y is equal to 24 x, y, 0 less than x, 0 to 1, 0 less than y less than 1, and x plus y less than 1, and 0 otherwise. So this is my joint PDF function. So that tells me that f of x, y would be the probability x is equal to x and y is equal to y, and it's calculated by this formula right here, provided that the ordered pair x, y is in the set that's defined by these conditions. Now, I think it's more than likely a good idea to just take a gander at the xy plane and see what those conditions are. So we could let that be an x-axis, and this can be a y-axis. and this of course would be 0, and it would run out to 1 there, and up to 1 there. So these are conditions on x and y. Y has to be between 0 and 1, and x has to be between 0 and 1. But that's not the only condition. There's also another condition that x plus y has got to be less than 1. Now, let's figure out what the boundary looks like for x plus y less than 1. So the boundary would be y equal minus x plus 1. And I've written it that way because this is a linear equation we recognize, and it has slope -1 and intercept +1. So this would be the line. Let me see if I can get a little better at drawing it. Well, in the end, I moved just a little bit anyway. This would be the boundary of the region where the fxy function is non-zero. Now, which side of this does this set right here, which side of the boundary is that set on? Well, easy thing is just to pick a point out here. Let's pick 0, which we know is on the bottom side of this line. Now, is 0 satisfying x plus y less than 1? Or on the other side, it'd be x plus y greater than 1. Well, 0 plus 0 is 0. That's less than 1. So I know that in fact, this is the region on which f of xy is non-zero. All right, so we've got an idea of that now. Now let's find the probability that x plus y is less than 1/2. Well, I know from the definition of the joint PDF that a probability like this, ordered pairs x, y in a set A, would be the double integral over the set A. So the next thing we probably should do is to figure out what region of ordered pairs x and y would satisfy this inequality. So I know that x plus y has got to be less than 1/2. Well, that tells me that y, the boundary anyway, the boundary y would equal negative x plus 1/2. And just as we did before, we can plot this boundary. So this boundary would have slope of -1. It's going to be parallel to the line we just put up there, but intercept of 1/2. So the intercept would be right here at 1/2, and this would be 1/2 down here. And so I'm going to put my cursor about there, and so there's the boundary of the region that satisfies x plus y less than 1/2. Now the region itself is on which side? On the top side or on the bottom side? Same trick, just pick any point, and 0 is convenient. 0 plus 0 is in fact less than 1/2, and so I know that I want to integrate over this area right here. That's not a very striking color there to use. I want to integrate over that area right there. Now it's going to be an iterated integral, and so we can integrate first with x and then with y, or the other way around. But I want to let, first of all, I want to let x go from here over to here, like that. So we need to figure out what the limits are going to be on x. So that just means we need to figure out, for a point here, what's its x coordinate. So I can use this equation right here and just transform it to x is equal to 1/2 minus y. Now, you've all been through calculus, and so this is review, but you might not have done it for a while. So let's go ahead and say that the probability that x plus y is less than 1/2 is equal to the integral of the integral from 0, that's where x starts at 0, and goes to 1/2 minus y. And this would be f of xy, and that f of xy is the function over this interval. It's the function, forgive me, I forgot, but it's 24 xy. And then I'm going to integrate with respect to x, followed by with respect to y. And the limits on y would run from 0 to 1/2. So this would be 0 to 1/2. Now, when I'm integrating with respect to x, and if it helps you remember, we could put these symbols of aggregation in. If I'm integrating with respect to x, the 24y would be constant and can come out. So this would be equal to, and in fact I can take the 24 clear out here, integral 0 to 1/2 y, and then in here I would have the integral x dx. This would be 0 to 1/2 minus y, and then dy. So it's a quick review of iterated integrals. We're going to integrate this and get an x squared by 2, and then substitute upper and lower limits. Lower limit's 0, so that won't really give us anything. And then I've got an expression in y that I have to multiply by this y, and I wind up with, just to kind of jump in here, and I hope in my notes I can find where I'm jumping to, 1/2, and this looks like 24, I think this is y by 4 minus y squared plus y cubed dy. And then this is just a single integral, and so you know how to integrate those things. And when you finish this, it is 1/16. So you can see if you can finish that integral and come up with the same value that I came up with. So here's an example of joint probability distribution using a continuous PDF. And it's sort of like the discrete case, but you get to use integrals instead of summation. So I think that will finish this topic for right now. This is part 3 of the joint probability distribution. And so we will hang it up for right now. But we'll be back later. Thank you.